be going through a schematic and building a fault tree from that schematic. On the phone, I have myself, Jeremy Henick. Let me actually start this. And Joe Bellin from our technical support team. Joe, are you there?
Yes, hi.
Okay. Just a few things before we get started. Today we'll be working primarily in our reliability workbench software, although some of you I know use our availability workbench software. A lot of the logic in building the diagrams from the schematic will be the same. So even if you are using the availability workbench, you still benefit from this presentation. Questions. If you have questions that come up during the meeting, there are a large number of attendees to this meeting, so everybody's muted. We wouldn't be able to hear anything if everybody was unmuted. So if you have any questions, you'll see a GoToWebinar toolbar on the right-hand side of your screen. Please post your questions under questions or send them to me in chat. And I will either answer your questions directly or Joe will be pausing from time to time throughout the meeting to answer questions. And so I'll ask him questions that might pertain to everybody. Everything else I'll answer privately, or if it's a detailed response, I'll send it to you after the meeting. I am recording this meeting, so after the webinar, I'll be sending out a link to everybody. All you need to do is click on the GoToWebinar link, and it'll ask for your name, and it'll give you access to a recording of this meeting. And this is the schematic. However, I'm going to actually turn controls over to Joe, who will be explaining the schematic and doing the majority of this presentation. Joe, I'm just passing controls to you now. You got that?
Yeah, let me just share my screen. Okay, and let me share that schematic again. Okay. So I think Jeremy sent out a quick description of the schematic, but I'll go through it just to explain. The schematic on its own is sometimes hard to understand. So just to give a little bit of background, this is a simplified example taken from our fault tree training. For those of you who've been in our fault tree training course, it might look a little bit familiar. You might recognize it from the training notes. We'll just go through and explain what this represents and how it works. It represents a chemical reactor vessel which has the function of mixing two chemicals that come in through via inputs 1 and 2 to produce a product and a byproduct. Now, if this reaction, this chemical reaction, is not properly maintained, a runaway reaction can occur, which can cause a safety or a hazard. If the runaway reaction occurs, there will be an increase in pressure and temperature, which risks rupturing the reactor vessel. And that's obviously very bad, and we don't want it to happen. So there is a safety system put in place that is supposed to automatically engage and prevent that runaway reaction from leading to a rupture of the reactor vessel. So shown on the schematic are only those components that are part of that emergency shutdown safety system. So let me just explain how the safety system works. In the event of a runaway reaction, that will cause an increase in temperature and pressure. So we have two sensors, a temperature sensor, PS, and a pressure sensor, PS, which will detect those elevated levels. When they do detect, and there's the provision for two of them is as a redundancy. Only one of the sensors needs to detect the unsafe levels in order to start the shutdown process. Now, when they do detect the runaway reaction is beginning, they'll do two things. One is they'll send a signal to the controller, which will tell the program to shut down electric valve 1 and shut down electric valve 2, or to close those two valves. They will also signal the alarm, which tells the operator to shut manual valve 1 and manual valve 2. The provision for both the electric and manual valves is, again, as a redundancy. Only one of the valves on a given input line needs to be shut. So only the manual valve or the electric valve need to be shut in order to halt the reaction. However, both input lines need to shut in order to cause the reaction. Should one of the inputs remain open, the runaway reaction will continue. In the event of that occurring, the runaway reaction continues because one of the inputs remains open. We have a fail-safe, a pressure relief valve that will vent the excess pressure in the reactor with will be a minor release of toxic chemicals. Should our pressure relief valve be stuck closed, and the runaway reaction continues because one of the inputs remains open, then that will lead to a rupture of the reactor vessel with the consequence of a major release of toxic chemicals. So what we'll be exploring today is using the fault tree module within Reliability Workbench to model the hazard failure to stop rupture of the reactor vessel. So we're going to first build that schematic within Reliability Workbench and show how that works. Now, basically what this webinar is going to be is sort of an advanced tips and tricks for building. Probably most of you are familiar with the Reliability Workbench and with the fault tree module. So you probably had the basics of adding events and adding gates and things like that. So what I'll try and do is I'm building the fault tree to represent the schematic. Is I'll show a few of the maybe the more advanced features, the helpful time-saving tips and tricks that you might not know about. So I'll try and highlight those. Okay, I'm going to have this schematic off on my right-hand monitor. I have a dual monitor setup, so you won't be able to see my schematic. You'll just be able to see my Reliability Workbench, but I'll be referencing back to it. Okay. I will be using today Reliability Workbench version 12.1. This is the most recent version of our tool. It was just released this past January. And for the first time, just a quick aside, for the first time, it's now available in a 64-bit version. Previously, all of Isograph's software has been as 32-bit applications. If you're not familiar with what the distinction is, it basically has to do primarily has to do with operating systems and how much memory is available to the operating system and to the program. So if you have a 64-bit versus a 32-bit version of Windows, basically that refers to how much memory Windows can use. Now that we have a 64-bit version of Reliability Workbench, the program is able to access more memory, and therefore you're able to run larger programs or run larger analyses. I'm currently just using the 32-bit version of Reliability Workbench. The schematic, the fault tree we're going to be building today is not large enough to warrant the full 64-bit version. For our Availability Workbench users, we do have a 64-bit version coming soon. We're still working on it, and it'll be released, I think, later this year. And that's the one where I think we'll actually benefit the most from a 64-bit version. That tends to run out of memory more quickly than Reliability Workbench. Okay, so now let's jump into building that fault tree. To get started, I'll need to add a new top gate. So we have that Add Top Gate toolbar button. Just click on that, and it will add my new top gate to the tree. You know, I mentioned that the schematic wouldn't be visible, but there's actually a way around that. I can put the schematic on my screen so that you can all see it while I build from it. That's what the Reliability Workbench's bitmaps feature. You'll see in what we call the project hierarchy or project tree control on the left-hand side, there's this little bitmaps node that allows me to import picture files into my project, and I can display them on the screen. It could be something like a company logo or a picture of the system you're building, and that's what I'll be doing in this case, is that schematic. I'll click my Add Bitmap toolbar button, and so this will be the reactor schematic, chemical reactor. And I'll just browse for that file, and here I have that bitmap, that reactor bitmap file. It says bitmap, and it looks for bitmap files, but it can actually be any Windows image file, so PNG, JPEGs, GIFs, any commonly used Windows image file can be imported into the Reliability Workbench. So I'll click Open and tell it to resize the bitmap to fit whatever object I have on the screen. Click OK. Now it's in my project. To display it on the screen, it's very simple. I just add a new label into my fault tree diagram, and then I can just simply drag and drop the bitmap onto that label. Let me resize it to make it bigger so we can actually see what's going on here. There we go. So that's our schematic. I think it'll probably be a little bit small on your side, but it's enough to give me hints so I can remember what it is that I'm supposed to be building. Okay. Now, some guidelines on building the fault tree. When I described the safety shutdown system, I described it in the forwards perspective, starting with what happens and then what follows next. The reaction occurs, the sensors detect it, they send a signal, the valves shut. That's the way it's supposed to work. Fault trees are a deductive analysis, which implies a backwards thinking. So in order to build the fault tree, the simplest way to get started, particularly with a complex schematic or a complex system like this, it is easier to start with at the end, at the hazard, because that's what our top event will represent as our hazard, and work backwards to asking at each step, what is the failure that will cause this to occur? So I'm going to start at the very end with our failure hazard, fails to stop rupture. So that's what this top event will represent. I'm just going to edit this and call it rupture with a description of failure to stop rupture of the reactor vessel. Click OK. Now I'll just start building my fault tree by always just asking, okay, what will cause that, and look for the immediate causes. Obviously, we can see, failures of the sensors is going to have some impact. But that's going to be the very end, the very bottom part of the tree. I don't want to get there yet. I want to ask, what are the immediate causes of the system to fail to stop the rupture? Well, one of the immediate causes is the failure of the pressure relief valve. So let me add that as a basic event. And the other cause would be if the inputs remain open. Both of those things have to occur in order for the rupture to occur. So I'll add a new basic event and a new gate for those two things. Now, I'm going to be labeling these things as I go down. What you may have seen before where I double-clicked on the gate to open its edit dialog so I could give it an ID and a description. That can be cumbersome, and as we go through the tree, it would be annoying for me to have to double-click on every single item to be able to type into it. So here's your first trick that you can use is instead of entering information through program dialogues, we can get a tabular or grid view of all of the information that I want to enter. So I can use the diagram and grid right window mode option to display a table of information at the very bottom of the screen. This gives me an easy access way of adding text to my fault tree. When I'm in the grid view, I have an option of displaying different tables. So I'll choose which tables I want to display. So I'll show the primary events table. And by the way, what's displayed in here is keyed off of what's selected in the project hierarchy on the left-hand side. So if I select my top gate, it will show all events underneath my top gate. So right now it's showing my event EV1. This represents a failure of the pressure relief valve, NRV. There we go. That's much easier to type in here, and I can use the arrow keys or the enter key rather than having to go through dialogues. And you'll see how much time I'll save as I build up this fault tree. Let me jump over to my gates table. Now I can edit my gate. This represents a inputs not shut. Fails to shut down both inputs. Okay, now I can't directly set the gate type from here, but I can. This top gate here should be an AND gate, because both of these events both of these inputs have to occur. The relief valve must be stuck closed, and one of the inputs must remain open in order for the rupture to occur. So if I just double-click right here, it will open the gate properties dialog for my top event, and here I can choose the gate type. So I'll just set that as an AND gate, and it changes it up here, and we can move on. Okay, so failure to shut down both inputs. That would occur if, pretty simply, input 1 remains open or input 2 remains open. So I'll just add 2 new gates and label them as such. So I'll call this input 1, input 2. As you can tell, I'm not necessarily the best typist in a hurry. So let me, there we go. Let me just do a little correction of my spelling. Okay. Now, let me clear my add node, and we're going to start by continuing on input 1 remains open. But I'm going to, my fault tree is very quickly going to get large and a little bit cumbersome, so I'm going to break it onto a separate page. I'm going to bring the inputs to another page to make it easier to view the screen and get it to fit all together. So what I'm going to do is I'm going to check the page box for input 1. I'll need to double click here and paginate it. That means the inputs to this gate will appear on a separate page. I'm also going to take my schematic with me just by copying it and pasting it onto that other page. Select my gate, page down, and then paste my schematic so I can continue to see it while I work. Okay. So my input 1 remains open, and I need to continue working down from there. So why would input 1 remain open? Well, the electric valve would have to be open, and the manual valve would have to be open. They're redundant to each other. So long as one of them closes, the input shuts. And so both of them failing to close, both of them remaining open, would cause the input to remain open. So let me add gates for that. Input 1. Okay, let me also select it in the project hierarchy so I can see it down here. So GT1, this will be electric 1. Electric valve 1 remains open. This will be manual 1. Manual valve 1 remains open. Okay, with me so far. Continuing down, let's just start with the electric valve. Why would electric valve 1 remain open? Well, either it has failed, it's stuck open, an actual physical failure of the valve, or it's not receiving the signal from the controller to close. Or there's actually another one, I failed to mention it in my description. The electric valves are actually powered from the grid. So if there's a power outage, the grid failure would also cause the electric valves to fail to shut. For this system, the grid is, we're only considering the grid as an input to the electric valves. Everything else has its own independent power supply or battery backup. So the controller or the sensors all have their own separate power supplies. So let me just continue here. Before I continue, this should be an AND gate, correct? They both have to remain open. So let me just double click here. By the way, I learned this pretty quickly from working with it. When you click on this drop down here for the gate type, this is standard for any Windows drop down list. You can usually hit a key on the keyboard to select the first item that starts with that letter. So I press A, it selects AND, O will do OR, I doesn't hit it. So actually the fastest way to change this, just click and then press the first letter of the gate type you want. So I go click and then press A, changes it to AND gate, and then I can click again. And I've gotten really good at, well, you'll see me do this as we go on to change the gate types. I can do it in just a couple seconds that way. Okay, input 1 remains open as an AND gate. Okay, let's continue down from the electrical valve. It's stuck closed, the grid has failed, or there's no signal from the controller, and that's going to be a separate gate. We'll build that up later. Okay, let me just first name this one. I'll call this controller. Okay, let me jump back to my events table and name these EV1. Well, that's actually what I want to call it. This is electric valve 1. Stuck open, actually. I'll just call it fails. Electric valve 1 fails open. If you're wondering what key I'm pressing, because you can't see my keystrokes, if you're wondering what key I'm pressing to edit a field, it's actually the same key. Again, it's a standard Windows key. You can use this in Microsoft Excel. If you press F2 on your keyboard, it goes to edit mode for that field. So rather than having to click on it to be able to edit it, you can just use your keyboard F2 as a shortcut. We'll call this grid supply failure or outage. Okay. Continuing down in our schematic, no signal from the controller. Let me move this down a level so we can continue to watch it. No signal from the controller if the controller has failed or there's no signal from the sensors. So I'll have a basic event for the controller and a gate for the sensors. And I'll just continue all the way down to the individual sensor failures themselves. No signal from the sensors if both the temperature sensor and the pressure sensor have failed. So I'll just create the basic events for those. Clear add mode and then label everything. Then EV2 is the controller itself. EV3 and 4 are the pressure transmitter and the temperature sensor. Okay, and then let me jump over to my gates table. This will be sensors, no signal from sensors. There we go. And this should be an AND gate because remember the sensors are redundant to each other. So let me just do that, change it to an AND gate. Signal from sensors. There we go. See, that's how quickly you can change a gate type when you have when you use the keyboard shortcuts. Okay. Makes sense so far? Everybody with me so far? Now we need to build up the other half, the manual side of it. I'm just going to reposition everything and put my schematic. Okay, so why would the manual valve remain open? Well, it could be stuck, or the operator doesn't act to shut it. So let me label those. Operator does not respond. And go to primary events. This would be MV1. Manual valve 1 fails open. Okay. Building down, why would the operator not respond? You know, I've been using this example in our training courses for about 11 years now, and I've put a lot of thought into that. And I think the conclusion I've come to is that our operator is Homer Simpson, and he's just asleep on the job or out getting donuts or something. So operator would not respond because he's unavailable or because he's Homer Simpson. And the other cause would be he didn't hear the alarm or the alarm didn't sound. So that'll be its own, actually that'll be a gate for the alarm doesn't sound. So let me continue this. EV2 is operator unavailable. And the this input here would be, well, let me jump over my gates table. Alarm does not sound. We'll call it alarm unit. Alarm does not sound because the causes of that, again, working backwards, either it has failed or there's no signal from the sensors. Because remember, the same sensors signal the alarm and the controller. Now, what we might be tempted to do is add a new gate here and then add new basic events for the pressure sensor and the temperature sensor. Well, no, that's wrong. It's the same temperature sensor and pressure sensor that signal the alarm as that signal the controller, which means we need to use the same basic events to do that. Now, you might be familiar with a copy and paste for accomplishing that. There's another easy way as well, and that's with the add existing feature. So right now I've selected the add gate mode. And so far I've been left-clicking to add a new gate or event. Instead of doing that, I'm going to right-click. Now when I watch what happens here, alarm does not sound, I right-click. And it pops up the gate selection dialog asking me to choose an ID or choose a gate, an existing gate to add. So it's going to be the sensors, because it's the same sensors that power that signal the alarm as the controller. You can also use the filter. If you've got a big long list, you can just start typing in sensors, and it automatically filters down to that one. So I clicked OK, and now I have, notice the transfer in symbol with a little line underneath it. That means it's the same gate. You can see it's the same ID that appears in both places. That's what lets me know that's the same sensors that signal the controller as the alarm. And this is important for the calculations because if the sensors are unavailable, it affects both the electric and manual valves. That's why I wanted to make sure I entered the same basic events, the same linked basic events in both cases. Okay, let me just do this last little bit. This needs to be named EV2. This is the alarm failure, right? There we go. Now let me hide the grid, and we'll just take a look at this, make sure I've entered it correctly based on my schematic. Just review it for a second. Okay, let's just look. The input remains open if both the electric and manual valve remain open. Electric valve would remain open if it's failed, if there's no power supply from the grid or no signal from the controller. There would be no signal from the controller if the controller has failed or there's no signal from the sensors because they have both failed. Manual valve would remain open if it's stuck. Manual valve fails in the open position, or the operator does not respond in case he's unavailable, or the alarm doesn't sound, which would occur because it's failed, or there's, again, no signal from the sensors. Okay. That makes sense so far? So now let's go back up. We've already built up input 1, so now we need to do the same thing for building input 2. Now here's another trick that you can use. You can see that input 2 is basically identical. It's all the same components. The sensors, the alarm, the operator, the controller, the grid are all the same between input 1 and input 2. Really the only thing that's going to be different is the valves, individual valves themselves. Now we could either rebuild this whole structure from scratch, which we just did a whole lot of work. Let's save ourselves the effort and use another handy feature of reliability work bench. That's the copy and paste special feature. To do this, I'm going to delete this gate here, and I'm going to copy and paste input 1 in order to create the input 2 link. So I'm going to hit copy, select the parent, and now I'm going to press paste special. And I would definitely want the paste special and not the paste option. The paste option would be very wrong in this case. I want paste special. Now paste special allows me to take some items in my fault tree and copy them in the data in them into new items. However, when I paste special on a gate, I can tell the program that some of the items should be the same, should be shared between the two gates, or between the gates that have original gate and the new gate that I'm pasting. So since it's the same controller, the same sensors, the same operator, the same alarm unit, I'll tell the program those should have the same, I'm telling it I do not wish to rename them. These should be the same between the original and the new copy that I'm making. Same thing for the events. The grid, the controller, the pressure transmitter, the temperature sensor. Oh, and by the way, I should mention I'm holding down the control key on my keyboard while I click on them to get it to multi-select. All of these, again, are the same components. So I'm telling it not to rename these. I only want it to rename the electric valves. Okay. I click OK. Creates it. And notice it also automatically incremented the names of the gates and the items that were not renamed. So input 1, it automatically incremented it to input 2, and that's exactly what I wanted it to do. Same thing, electric 1 became electric 2, electric EV1 became EV2, but everything else is the same. Same controller, same operator, same alarm unit, same sensors, etc. So you can see how I just saved myself a ton of effort using that paste special option. Okay. The one thing it didn't change was the descriptions. You'll see it didn't increment that. So I could either go through manually editing in that way, or this actually might be a good time for the diagram and grid. I can actually use the find and replace option. Find the number 1 in the description field and replace it with the number 2. So find first EV2. I'll replace that, so it's now electric valve 2, and find the next one, MV2. I'll replace that in the description. It's updated from manual valve 1 to manual valve 2. There we go. And then I can do the same thing for my gates. Use a find and replace to automatically change the description. Find 1 in the description field and change it to 2. I'll just do a replace all this time. It tells me that 3 replacements were made. And you can see on the diagram, they just automatically changed. Okay. We'll take our first break for questions right here. Were there any questions on any of this fault tree construction process? Is there anything I did that you want a little bit more information on, or you want me to go through again? Jeremy, have there been any questions so far?
Yeah, maybe we should kind of give like a simple explanation between paste and paste special. When you rename your block, it's copy of a block that's renamed, the system's recognizing it as a duplicate system, not the same system, right?
Right, that's paste special. So I'll show it on a basic event. I'll just take my non-return valve. If I do copy and paste special, notice the name was changed. This is NRV, this is NRV1. So it took all of the information in this basic event and put it into a new one. When it runs the calculations, it will treat this as a separate basic event. So it's as if it was a distinct failure event. When I do copy and paste regular here, notice it's the same name between the two of them. So it's basically, that means it's the same thing that appears in multiple places. And actually, they're linked to each other. If I edit it in one place, so for instance, if I change the color of my event, it changes it in both places that it appears because it's the same one in both places. Let me reset that to default. Also, when it runs the calculations, it will treat it as the same failure event in the cut sets. So there's no redundancy between these items. If it's failed in one place, it's failed in all places. So that's how it works for basic events. It's essentially the same for gates. When you paste regular a gate, it means it's the same branch. That's what I did for the sensors. It's the same items that appear in different places. If you paste special, you're just creating a new branch that's similar to the old one. Does that make sense?
Yeah. Yeah, it makes sense.
Okay. Any other questions before we move on?
Some are, most of the questions are a little complex. The more in-depth questions I'll be answering privately, or we'll bring them up if we have time. Some of these questions are a little in-depth for a web meeting.
Sure, okay. So the more complex ones, we can even answer after the web meeting is over. Jeremy will send them to me, and I'll respond via email. Okay, but we need to move on. Let me just show a couple other possible ways of building this same fault tree. I have on my alternate monitor, let me drag this over. Here's another way of building the fault tree. Fails to stop rupture if the valve is stuck, and fails to halt the runaway reaction, which would occur if it fails to detect the runaway reaction or fails to shut down the input. So basically here what I've done is I've broken the sensors off and moved them up to the top. But underneath here we basically have the same thing, fails to shut down both inputs if input 1 is not shut or input 2 is not shut. Okay, so this is just an alternate way of doing it. I've just pulled out the sensors and moved them higher up in the fault tree. And this sometimes makes a little more sense. This is the way safety systems are more commonly constructed. The fault tree, you have your inputs, in other words, your sensors, and you have your outputs, in other words, the shut-off valves or the actuators or whatever, the pump power removal or something like that. Okay, let me show you an incorrect way of doing it. Here's another similar way of doing it, emergency shutdown system failure, no signal from the sensors, or the failure to shut down the inputs. But here I've done it wrong. But this is we have a really strong driving need to do it this way for engineers. We want to model the electric system on one side and the manual system on another side. Unfortunately, it just doesn't work in this system. Here I've broken it down. Fails to shut down inputs if the manual valves are not shut, and let's say, well, they're redundant to each other, right? There's a manual valve and an electric valve that provide redundancy to each other. Those two systems exist for redundancy. So put an AND gate, and then say, and the electric valves are not shut. Unfortunately, I can't really isolate them that way. They're really firmly embedded with each other. Manual valve 1 is redundant to electric valve 1, but not electric valve 2. So now how do I tell whether or not it's the right or the wrong answer? That would be obtained via a cut set analysis. Let me go back to my correct answer. I'm going to turn on my cut set analysis. Ignore this, these options right now. It's just turning on the cut set calculations. And then I can take a look at the results. This is just going to be a purely qualitative analysis to get a feel for the cut sets. Here's a list of all the failure combinations that would result in a failure to stop the rupture. You can see I have 15 cut sets. Comparing this to another tree will tell me whether or not that other tree is correct. Here I have 17 cut sets, so that tells me there's something off. Really, the reason that I have these extra cut sets, here it says a failure will occur if the non-return valve fails and manual valve 1 fails and electric valve 2 fails. But in reality, that's not really the case. Let me go back to the schematic. If electric valve 1 fails and manual valve 2 fails and nothing else, we'll still shut down both inputs. So this is an incorrect way of solving this particular problem. And it's because of, in this particular example, the manual valves and electrical valves are enmeshed with each other, that we can't separate them into separate branches. Okay, the next step, I'll try and move a little more quickly. I promised to be done by 11 o'clock, and there's a lot more features I want to show. The next thing I'll show is the adding failure information. So far, we've run a qualitative analysis. So let me save my work so far. In case the worst happens, in case my computer fails or something like that. Now what I want to do is I want to add failure information to this tree so I can perform a quantitative analysis. Here's the, I'll just quickly show it. Here's the table of failure information for each basic event that I'm going to be using. So for each event, here's the failure model type that I want to be using and its failure information. Okay, so different failure model types have different failure information. I'm just showing this right now. Again, I'm going to have it on my second monitor. You're not able to see that table while I'm constructing it. But afterwards, if you'd like to try this on your own, I can send you that information. I can send you that table of failure information. Okay. So the first thing I want to do is I want to be able to set up the units. By default, units are unspecified within Reliability Workbench. It means the program doesn't really care what units you're using. Just so long as they're consistent, you have to be entering the same units in every single place. I want to directly tell the program what units I will be using. So I'm going to uncheck that unspecified consistent option and tell it my failures will be in years and my times to repair will be in hours. Another thing I can do, let me just show that chart one more time. You'll notice most of my failure models are dormant model. So I want, whenever I add a new failure model, I want it to already have dormant selected. That way it saves me a few clicks of having to choose the failure model type. So right here, I will choose my default model type as dormant. Okay. Now I'm just basically going to be going down the list and adding failure models as appropriate. So for my power supply, my grid supply, I'll create a new local model. And that will be using the rate model as the only one that's using the rate model with a failure of 1 failure per year, and a repair rate of 1,000. This is kind of a weird unit, 1,000 repairs per year. That's not exactly the most intuitive of inputs, but 1,000 repairs per year means it basically takes about 8 hours to repair. Okay. The next one is the failures for the electric valves, electric valve 1 and the electric valve 2. Now to do those, I will actually create a generic model. Since they both use the same failure information, I'm going to create a new generic failure model. We'll call this just EV for my electric valves. Referencing my table, I have a failure rate of 0.7 per year, time to repair of 48 hours, and a test interval of 1 year. Okay. Now I'm just going to go as quickly as I can through the rest of them. It's always a little tedious adding failure models, so I'm going to do it quickly. Okay. By the way, you can do this from the grid control. You can add generic models in the grid control as well. This is for my manual valves. And actually, let me just do that. The thing is, though, if you do it from the grid control, if I show failure models here, and there's an insert option, add record, insert, it still pops up this dialog. So you still have to enter them through here. Although you can edit their failure property, the failure parameters from here. But anyway, most of the rest of these are local models, so I'm just going to be creating local models for each. Controller, temperature sensor. Pressures transmitter. Okay. Sorry that I actually probably should have pre-prepared these beforehand, but I wanted to make sure that I didn't skip over anything. So. Alarm the non-return valve. We only have 2 more, so bear with me. NRV, 0.05, 8, and lastly is the operator. He uses a fixed model, a fixed unavailability of 0.1. Okay. One last thing is I did not actually assign these models to the relevant basic events. One way of doing that is just you can edit the event. So I'll edit electric valve 1, and I can choose an existing generic model from the list there by clicking the binoculars. I did the same thing for MV1. The other, actually, I think, easier way would be find the basic events in the tree. So here they are, EV2 and MV2. You can just simply drag and drop. There you go, onto the basic events. Now, let me save it. Notice it's showing the failure parameters. If I want to see what failure models are attached, I can go to my view options. There's a couple other options I might want to show. Show failure repair and failure model IDs. And it shows a little bit more information underneath the basic events. The name of the failure model that's attached, so I can make sure it's the correct one. In case you're like me and you accidentally click and drag the wrong one, you can see easily which one's attached. And you also see your parameters, your attached parameters. Okay. So there we go. That's all it takes to add failure information. So now we can run the analysis and get the results. Before I do, let me just set up a few of the project options. Save it first. These are all set. On the calculation tab, I want to examine it over a, let's say, a 20-year life. I'll leave off MTBF calculations just for the sake of speed. That's not really what I'm most interested in here. And I'll leave most of the options at default. So I'll click OK. Click Perform the Analysis. And when it's completed, it will show me the unavailability underneath my top gate, and I can view extra results for the top gate. How often does the failure occur? Number of expected failures over the 20-year period, the unreliability, etc. So there's my results for my fault tree. So what this is basically telling me, unavailability of 0.006712 means at the end of the lifetime, there's about a 0.6% chance the system would fail to be able to stop a rupture should it occur. Should the runaway reaction begin, I should say. Okay, let's take our second break for questions there. Jeremy, has there been any questions on the adding failure data or adding quantitative data portion?
Yeah, can you drag and drop the failure data into the model?
Drag and drop failure data into the failure model itself?
Yeah.
No, it's always typed directly into this model here.
Also, there still seems to be several questions about a paste and pay special. What we'll have to do is contact those of you with questions offline. It's just a matter of maybe understanding the calculations and what the difference between the same component and a duplicate component in what may be copies of the same branch or duplicate branches.
Yeah.
So those questions we'll address offline.
Sure.
The rest of you, I'm getting to your questions kind of in chronological order, so I'll just continue answering those.
Okay, let's just move on. There's just a couple more things I want to get through. So what we've got here, sometimes, for those of you from safety systems or who work with safety instrumented systems or safety instrumented functions, you'll probably recognize this as the PFD, probability of failure on demand. It represents that the probability that should a runaway reaction occur, what's the probability that we can't stop it and it will lead to a rupture of the reactor vessel. Sometimes people want to go a little bit farther than that. They want to know actually how frequently will that rupture actually occur given a frequency of runaway reactions. This is where we might use an event tree to quantify it. The other thing that some of you might ask is, okay, failure to stop rupture is obviously bad. I said that's a major release of toxic chemicals at the beginning. But sometimes you might ask, well, you'll notice this pressure relief valve option. If we fail to shut down both inputs, we vent through the pressure relief, and there's a release of toxic chemicals. There might be, environmental penalties, or the EPA might get on our case about that. So we want to mitigate that and know how often that occurs as well. One of the things I can do is if I retain the results for this gate, then I can view how often, or the PFD for the failure to shut down both inputs. So I can get a separate PFD for that. But what I want to know is I want to be able to rank and compare these hazards, the minor release versus the major release. How often do they occur, and what's the risk associated with each one? And that's where I might use an event tree. I'm going to just jump over to my event tree module and build a very simple event tree using this fault tree as a basis. Add a new event tree. This is for the runaway reaction. There's going to be 3 columns. Okay. The initiating column is the runaway reaction occurs, so I'll create a new basic event to associate with that column. So I'll call this runaway reaction, or just runaway. And I'll just say, I think I was looking at my material earlier today, and the frequency in our training material was 0.2 occurrences per year. So about once every 5 years, the conditions for a runaway reaction occur. Okay. Now to associate that with the column, let me give it a description. I'll just simply drag and drop it onto the initiating event, or the initiating column of the event tree. My next column will be the failure to shut down both inputs. So what I'm going to do is I'm going to edit this and choose that gate using the binoculars. What was it called? Inputs. Fails to shut down both inputs. There we go. Apply it to my column. And the last one was the will be the basic event for the non-return valve. Pressure relief valve stuck closed. Okay, so basically, let me turn on the branch type. So you can see the true and failure and success branches. So basically, this runaway reaction occurs, fails to shut down both inputs, and the pressure relief valve stuck closed. That's the chain of events that would lead to a major release of toxic chemicals. If the runaway reaction occurs, there's a failure to shut down both inputs, but the pressure relief valve is able to successfully open, that will lead to a minor release of toxic chemicals. It's still bad, but not as bad. So I want to know how often those two things occur. I don't really care what happens up here, so I'm going to just delete that branch. Just only consider the failure to shut down both inputs. Let me create 2 consequences, 2 environmental consequences. And I'll say our risk, our consequences in terms of tons of toxic material released. We'll say that a major release, we'll call this major release of toxic chemicals, would release, say, 10 tons of toxic material into the atmosphere. That would be if a rupture occurs, everything inside the reactor vessel spills out. You release 10 tons of material. For my minor, I'll create a second consequence of minor release. I'll say only half a ton. If we just vent it, but preserve the reactor vessel, the relief valve opens to vent the runaway reaction. We have a more minor half a ton. I can apply these to the final branches, again, simply by dragging and dropping, major release, minor release. And that's the event tree. That's all it took to build the event tree from it. Save it, perform the analysis. And what I get at the end is the frequency of each outcome in terms of years. So 0.001 years So a little less often than, or a little more frequently than once every 1,000 years. This one is a little more frequently than once every 20 years. I can view the point risk from the results summary. I view my chain by selection up here to risk. I can view my environmental risks. What it does to calculate risk is it takes frequency, multiplies it by the tons of material, and get my point risk, which essentially represents the tons of material released per year. Summing up for the category, the point risk for my environmental category gives me from all consequences the total tons released per year. So I've got 0.04 tons per year. Suppose we've been given a goal, maybe an industry regulation. The EPA might have given this goal. It might have come from management, from their safety supervisors. Suppose they've assigned us a goal of 0.1 tons per year. How would we go about finding the best way to meet that? And before we answer that question, I'm going to pause again to ask if there are any questions on the event tree.
Yeah, there's a couple. The frequency, is that the same frequency that's listed in the fault tree module?
Yes, if you're using a fixed model, basic event model, or if you look at the results summary for a gate and it shows the frequency, it's the same frequency as the as calculated by event tree. It's basically how often does it occur. We can actually see that for our major consequence. We can see the frequency, how often does it occur per year. Okay. Next question.
We're running low on time here. I'll ask another one. Maybe we can discuss the frequency. Let's see. I think the frequency is listed in years, right?
In this particular example, yes, because I chose my unit says years, my failure unit says years. So for my fault tree gate, it gives the frequency in years. For my event tree, it will show it in years. Yes.
Okay.
Okay.
As I mentioned before, there's a lot of questions coming in. Probably most of these questions we'll have to address offline by emailing you individually.
Sure. Okay. So let's last thing we'll do, I just asked a question, and I'll go through this as quickly as possible in our last 5 minutes. The question was, how can we figure out how to get this risk below the goal that we've set for ourselves? We want to have no more than 0.01 tons per year. So how do we do that? First thing we'll look at is the importance analysis. This tells us what's the biggest contributor to, actually, oh, you know what? I'm going to do set a little option and rerun. I don't want to modularize. Okay, that's what I want to do. Now I can look at the importance analysis, and we'll find out what's the biggest contributor to our failures. So we can see the electric valves, the manual valves, and the non-return valve are actually all high Fussell-Weasley importance contributors. What that means is basically what percentage of the failures involve the occurrence of that event. So electric valve 1, EV1 having a Fussell-Weasley importance of 46.19 means that 46.19% of the environmental occurrences involve the fails open of electric valve 1. Okay. So that would give us a good place to start. If we improve actually all of our valves have a very high Fussell-Weasley importance. That's where we want to start looking. Now, again, those of you who work with this type of safety system, CIFs or IEC 61508, 511, will know exactly what we need to do. We want to try different test intervals. I went through it very quickly when I was creating the failure models, but everything's tested at a frequency of 1 year. Maybe if we tested more frequently than that, we'd have less outage time, less downtime. So I want to find out how frequently do I need to test in order to meet my goal. I'm going to do something pretty quickly here. I'm going to assign a generic parameter to all of my valves for the purposes of doing a special sensitivity analysis. So the first thing I'm going to do is create a new generic parameter. We'll call this the valve test. It'll be how often am I testing my valves. I will use the value 0.08333. If you're wondering why that value, that's 1 month in units of years. 1 month is 0.08333 repeating years. There's a reason I'm doing it. There's a method to my madness, which will become apparent as I go through it. The next thing I want to do is assign that generic parameter to all of my valves. So I'm going to go through each event. And here's just one quirk of the program. Generic parameters can only be assigned to local models. So I'm going to have to assign a local model to each of my valves. For the non-return valve, I was already using a local model. So for these, they're using generic, but if I click the Create a New Local Failure Model, it will create a new local model with the same parameters as the previously attached generic model. So then I can just assign that generic test interval. And go do the others quickly as well. This is MV1. EV2 and MV2 are next. You can see you can actually get through it pretty quickly, creating the local models. Okay, there we go. So now this generic parameter is assigned to all 5 of my valves. What this means is I can change this test interval in one place at the generic parameter level, and it will automatically apply to all of the valves that use that generic parameter. More importantly, I can use this for my, I'm going to rerun the analysis just to get up to date. I can use this in my special sensitivity analysis. I have, my clock shows 1 minute left, so I'm going to go through this quickly. What I'm going to tell the program to do is modify that generic parameter, try a range of different test intervals, and see how that impacts my environmental risk. So I'm going to see how the impact on frequency when I change my test interval. I'm going to try, what did I do? I think I did 8 when I was doing my dry run. 8 different factors, 8 different test intervals that I want us to test. And because I set my test intervals at intervals of 1 month, my factors represent months between tests. So I test every month, every 2 months, every 3, 4, 6, 8, 9, and every year. So I'm going to get a range of different outcomes for my sensitivity analysis. And on the results, what this will show me is the frequency, or actually I think it's what it ends up showing me is the risk level for testing at different intervals. So I test every year. It's 0.03991, which is the 0.04 that we saw in the result. I want to find out when does it drop below 0.01. That was the goal we set for ourselves. And it turns out if I test every 4 months, then it will be meeting that goal. Okay, that's what this tells us right here. Each one of these columns represents a different test interval. This times 1, times 2. Those are basically the number of months between tests. Okay, so if I test my valves, do my whatever testing I have on them every 4 months, then I will meet my goal. Let's set that up. 4 months is 0.333 years. Rerun the analysis. Go to my results. And my point risk is 0.008986 tons of material released per year. Okay. That takes us to the end of the time that a lot of time we have. I'm sorry I don't have enough questions or enough time for questions on the special sensitivity analysis. If you have any, please email me or Jeremy, and we will respond via email. Or if it's a more complex question, we can even give you a call if we need to talk about it. Although there are a lot of you in the meeting, so give us a little bit of time to get to respond to all of your questions. Thanks for attending, Jeremy. Is there anything you wanted to say in conclusion?
Yeah, here I'm just going to take this really quick. All of the questions that came in, we will respond to each of you. There was quite a few questions that came in. We could probably spend all day on this model, just going through different options and things that you could do with it. But this was designed as, actually it wasn't even designed as an hour meeting. It just ended up being an hour. If you have any ideas for future webinars, we plan on having an upcoming webinar on reporting. We can do webinars on any of the types of models that ISOGRAPH offers. So if you have any questions or recommendations, please feel free to contact me. We'll be sending out a link with answers to the questions that came in, as well as a copy of the recording. And I thank you for attending today's webinar. Thanks.
Thank you.